and then we can compute this integral. It's very trivial. We find that this integral is 1, this is 1, and this is 0. So v1 is equal to 2. So now we have computed this element of the matrix. Let's turn to the element a v1 v2 v1. We write this integral because that's the definition of this bilinear form, and as I told you earlier, lambda is 1 in all these 3 intervals. We have to split this integral into 3 integrals and add them. And in the first integral, v1 was constant, so the derivative is 0. In the second interval, the derivative was equal to 1. So you write 1 here, and in the last interval the derivative was minus 1, and so on. In this, as we have told you earlier, the derivative of v1 is equal to 1, minus 1, and 0 in these 3 intervals respectively. So then we get easy integrals because we are integrating just a constant. This integral is 0, this integral is minus 1, and the third integral is 0. So we obtain that a v2 v1 is equal to minus 1. So then we have computed this element of the matrix also. Let us now compute a v2 v2, and this is done exactly as above. We just have to replace, we have to just write out the integral corresponding to a v2, and we easily get, using the same method, that this value is equal to 2. Moreover, we know that, as you know, this bilinear form is symmetric. So we know that a v2 v1 is equal to minus 1 also. So then we have all these 4 elements of the matrix, and now it remains to find the values of L of v1 and L of v2. We do it exactly as for the bilinear form. It's integral from 0 to 3 of f v1. This is just according to the definition of L v1. So we are splitting this integral into 3 different integrals, as we did when computing the bilinear form. And we know that in this interval from 1 to 0, f was equal to 1. In this interval, f was also equal to 1, and in the second interval, f was equal to 0. So inserting this, we get that this integral vanish, and we are left with these 2 integrals. So we are just computing the integral of 0 integral from 0 to 1 of v1, and how can we find this integral? It's in fact very trivial, because the integral of a positive function is just the area under the graph, between the x-axis and the graph. So computing this integral, we find that first we can, for example, just replace it by x in this um, region and taking the antiderivative of x and compute it. So we know that the integral here, since here we have shown you the graph of v1, we know that v1 is just equal to the function x in this from 0 to 1, and it's in this region it's equal to minus x plus 2. How is this the case? Just check it. You know that a straight line is possible to find the equation for the straight line is really trivial, and you can do it as an exercise, but it will be v1 is equal to minus x plus 2 in this interval. Just for checking, put x equal to 2 in here, then we should have 0, which we have, and we know that the slope is minus 1, so this must be the equation for this line. We here have computed the we know in order to find these equations, or this equation, for example, we just use that an arbitrary point y on this graph minus y1, and y1 we can choose any point on this line, but why not choose this point that we know for sure, y1 equal to 0, corresponding to x1 equal to 2. So just put this into here. We know that the slope is minus 1, so this multiplying now with x minus 2, we obtain this rather easily. Okay, this L of v1 is now, which we want to compute, is the integral from 0 to 1 of the function v1 in this area, which we have told you is x, and it's this expression in the second interval. So we can just compute these two integrals. The antiderivative of this function x is half square of x, and we put in the limits here, 0 and 1, and here we find the antiderivative of this function, and put the limits here. And it's really trivial to compute this integral. It turns out that L of v1 is equal to 1. So we can do the same for L of v2. Split this integral into 3 integrals and add them. We know that f is 1 and 1 and 0 in these 3 intervals respectively. And in the same way we find that we had to compute these 2 integrals, because this integral vanishes. And in the same way we find that v2 is equal to 0 in this interval. v2 is equal to x minus 1 in this interval, using exactly the same method for a straight line. We can find the equation for a straight line, this straight line, and here we have the expression for v2 in the interval 2 to 3. And computing the integrals, we obtain these that L of v1 is equal to the integral of v2, which is 0 in the first interval, plus the integral from 1 to 2 of x minus 1. And x minus 1, the antiderivative of it, is equal to this half x squared minus x, and then we add these limits and compute the integral easily and find that this is equal to 1/2. So now we have found all these parameters that we need. We have A xi equal to B, so this is A matrix and this is a B matrix, and then we can compute the we can multiply it with the inverse of the matrix. The inverse of this matrix turns out to be this matrix, and multiplied with 1/3. So our result is that xi vector is equal to, when we multiply this matrix with this vector, we get 5/6 and 4/6 here. So this is xi1 and this is xi2. And as we told you, UH, which is the finite element solution, is xi1 multiplied with the first basis vector plus xi2 multiplied with the second basis vector. So then we insert these two values and we have found this finite element solution. We showed you the graph of V1 and V2, and multiplying V1 with 5/6, we obtain this graph. Multiplying this basis function with 4/6, we get this function. And adding these two functions, we obtain the graph of UH. So here we see the solution, the general solution of the problem, which in fact in this case is possible. We can find this solution also, but generally it may be impossible to find it. But the numerical solution is possible to find. And if we now have chosen more refine this triangulation so that we get a larger space with more basis vectors, then we would have found a finite element solution which is even closer to the actual solution.